Okay, so good morning, everyone, and welcome to Lecture 23 of ECE3311, Principles of Communication Systems. In today's lecture, what we're going to be talking about is minimum shift keying, as well as Gaussian minimum shift keying, or MSK and GMSK. So let me adjust the camera. There we go. Excellent. Yeah, that's what happens when you have little children playing around with webcams. All right. So today's lecture, we're going to be talking about a type of modulation scheme that is used, frequently because it has a nice sort of continuous transition between one representation and another. All right. So we saw this before with respect to things like discontinuous FSK, right? So where if we try to communicate information, we had these abrupt changes between this is a 1, this is a 0, right? Now, binary 1 and binary 0 representation, which is two different frequencies. And this creates a lot of messiness, right? Because it has this like awful discontinuity between the two symbols. So what MSK does, is it tries to iron out those discontinuities in a very specific way. And we're going to be looking at that. And again, we're going to start with the premise, right? We're going to look at what discontinuous FSK looks like as a starting point. And then from there, we will proceed to implement MSK, all right? And it's not that difficult. It's not that difficult. Well, once you look at how it works, it's actually pretty straightforward. But there's a couple of basic equations that you need to look at. And then once you have that, like, you're off to the races, all right? Okay, so let's get started. Boop, boop, boop. All right. I'm going to iterate this again because I think this is going to be the last time we're going to be looking at these equations. So just like one last time, because essentially just for, later on when you're going to be using, when you're going to be designing or using modulation schemes, and you want to convert between the complex baseband and the passband, this is the expression you'll always be using, right? S of t. This is the mapping function of some message signal. Okay. And then it's modulated. Okay. And it's modulated to some carrier frequency, FC, right? And this is passband. Signal. And this G, okay, that's our complex baseband signal. All right. So we have these, this representation, okay? So let's revisit discontinuous FSK, right? And discontinuous FSK had something along these lines, right? So if you had a binary 1, you had a passband signal. It's not an I, it's a 1. There we go. That was equal to this. Moo, no. not passband. Silly. So we had something along these lines. So we had like omega 1 of t, and then we had some phase, right? G1 of t. And then we had G2 of t. Okay, and let me get my example. Okay, so I'm just getting my example ready for this. So what happens is we have this representation, and so now what happens is we had a binary 1 and a binary 0, right? And again, we saw what happened. Like, you know, when we have this, sometimes it might work well and sometimes it might not. But we had this like kind of abrupt change between, you know, let's say something that looked like every ts seconds. So remember, every symbol period right? And we might have something that looks like this. So let's say this represents a binary 1. And then let's say we had something that binary 0, and then abrupt change. So we lacked this beautiful transition. And we saw what happened when we had, you know, we actually used, we saw how we could make this continuous. We saw a way using an integral expression, right? If we used instead something like so. You might say what so was. And what we had was something, actually, I'm going back. This doesn't seem right because what happens is, yeah, no, that doesn't seem right at all. See, it's too early in the morning. Boom and boom, perfect. It should be yes, because yeah, how would you modulate the heck of that? No. So it would be, these would be passband signals, right? So what would happen is we saw how we did it continuously, right? We had something like this, right? We had some sort of frequency term. And then we had this beautiful, from minus infinity, right, to t, and then we had m of lambda, d of lambda, right? And then we close that. And this, remember, this was our phase term, right? That this whole thing, you might say, where the heck did Wyglinski get that from? And this is where I got it from, right? It would be, right? So this is how we would do either FM or PM, right? Plus there's a constant. I'm going to put C there, constant. Amplitude constant. And then it would be do. And there we go. And what would happen is this integral expression is really nice because it goes from minus infinity, and it kind of allows for a smooth transition of that phase term, right? And what it will do is it'll like allow for sort of the gradual, if we went from now, let's say, let's say a binary 0 had a faster frequency than a binary 1 every ts seconds, what we would have is something that would look like this, and then the frequency would progressively get faster. And then we would have binary 0, and then let's say we go back to binary 1, and then back to binary 0. So we had this like kind of transitional process between every ts seconds. And that was awesome, right? 0, ts, 2 ts, 3 ts, 4 ts. And what would happen is we would go from one frequency, let's say f1, to f2, to f1, to f2, and so on and so forth. So this was actually quite nice, right? Because we hate discontinuities. We absolutely hate discontinuities in the communications world, because that creates a lot of spectral, like unpleasantness, right? In terms of we don't want signals to go from minus infinity to infinity in the frequency domain because that causes interference. The spectral shape looks like garbage. We can't really contain anything. Overall, we don't want to do that, right? So with that in mind, okay, with that in mind, this sort of sets the groundwork for minimum shift keying. You might say, how so? How so, Wyglinski? How do you do that? How do you allow for minimum shift keying? Okay, this is what you do. All right. So first of all, let's switch gears. Let's go back to the slides, because I almost never go to the slides. I just ramble, right? Which I do anyway. So okay, remember that. Discontinuous FSK, bad when we have discontinuous symbols, as we just saw. Can we smooth out those transitions? Is it possible? So like, is there a way? Is there a way? Even like, please, please, please. Is there a way? This is one nice way. This is bad. This is bad. Especially if you look at something like this. It's like bzz, jump, bzz, jump. There's probably going to be a jump there, a jump there. Those are not nice. We want to avoid that. So is there a tricky way of getting around those? Yes, absolutely, 100% yes. Okay. So where are we? Okay. So this is the trick. Okay. This is a trick. This is the MSK trick. And MSK, I have to admit, MSK has been giving me kind of like running my mind through a loop. Okay, let's look at this thing. So suppose we have something like this. And again, this is very, I've been trying to wrap my mind around. So if I can, let me find the expression, because I don't want to leave all of you saying, what the hey? Okay, so I'm a graphical learner. Maybe a lot of you are out there as well. So the premise here is a little bit of like, this is how you set things up. So your M of T. So this is your message signal, not text message signal. No. What you do is your binary 1 gets mapped to an amplitude value of +1. Your binary 0 gets mapped to an amplitude value of -1. Okay, so keep that in mind. Step 1, right? So now what happens is, if you have a binary sequence, mu. Okay, so let's say we look for reference, refer to figure 5-34. Okay, so this is actually pretty cool. So here in your binary, in your textbook, it's kind of a nice graphical expression, but they have the data transmission. So let's work this out. This could be a great class test question. So they have a data transmission, and it is, let me decode it, 10100110110. Okay, so they had that. So we need to translate that into a waveform. So let's go to the next slide. What is it again? So draw a line. T. Okay, okie dokie. So 1010. Okay, let's start with that. So 1010. So far so good. And then 0110. Zero, 110. Okie dokie, perfect. And then 10. Okay, so this is the binary representation. So here, your M of T, okay? How does this look like? Side effects, sound effects included, right? Looks like this. And again, if I can draw properly. Let's do it again. Yeah, see, next time when I do these lectures, I should drink coffee before. Just kidding. Yeah, but the problem is, if you leave it on the burner a little too long, it tastes awful for the next person. Don't want that. Okay, so so this is a +1 amplitude value. That's a -1 amplitude value. This is actually super important because now what I'm going to do is I'm going to parse this thing out. Okay, how so? So what I'm going to do is I'm going to take this thing and I'm going to create x of t and y of t. How so? So this is the trick. So I'm going to take red. So let's say red, take 2. I'm going to take red. Yeah, that's it. And what I'm going to do is I am going to sample every second bit. Okay, so here, mirror. So here, very important, this is a bit period. We're using something other than symbol period? You betcha. So awesome sauce. So this corresponds to no, deep, 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 deep. Okay, great. So what I'm going to do is every second symbol, I'm going to sample. Perfectamundo. And do the same here. Zoop, 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 zoop. Did I get that right? Dup, dup, skip, 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 skip. Perfect. Okay, so that's blue. All right, and so the ingredients, if you're cooking, if you like cooking, is sample every second bit and hold for 2 TB. Wow. Okay, so this is actually pretty cool. So what I'm doing is I sample here, 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 and I hold the value not for 1 TB, but for 2 TB. This is actually really super duper important. Okay, so because what I'm effectively doing is something like this. Yeah, T. So now what I'm doing is that was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what I'm effectively doing is, what do I have? So let's actually do it for both. Same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. Yeah, 0, 1, 2. Yeah, shucks. So same thing. 0 TB, 2 TB, 3 TB. You get my picture. Same thing. 0 TB, 2 TB, all the way up to 10 TB. Now, this will be my x of t. This will be my y of t values. Funny thing, so heads up. X of t starts with a delay of TB. Okay, so this is actually super duper important. So there's going to be a first element that's like, hey, what do I do here? Okay, we leave that alone. Like, you know, we could even assume the value there, like plus whatever. It doesn't matter. The real value is going to happen with respect to whatever we sample at this instant, that instant, that instant, so on. So what it will be, let's say we look at x of t. So again, don't care about the first TB seconds. The second TB, absolutely, we 100% care. So it's going to be -1. We hold it not for 1 TB, we hold it for 2. So it's going to be -1. So let's do that. So it's going to be -1. Forget about this guy, right? -1, okay? Then +1, then -1, then -1. Okay, so let's do that. So it's going to be -1, -1, -1, -1, -1. All righty. So it's going to look like this. So again, we don't care about that. So this is going to be +1. That's going to be -1. It's going to be +1. That's going to be -1. So la 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 la. Oh, okay. So -1. Hold for 2 TB seconds. So what's the next guy? So it's going to be -1. So hold for another 2 TB seconds. Okay. Next guy, plus TB seconds. Hold for 2 TB. Then it's going to be -1 again for 2 TB seconds. And then it's going to be another 2 TB seconds. Alrighty. Okay. So next, what's the blue? Here we start immediately at 0, not TB. So it's going to be +1, +1, -1, +1, +1. Ooh, almost the opposite. Okay. So it's going to be +1. So hold for 2 TB seconds. +1. -1. +1. +1. Okay, so we've just created, okay, our x of t and y of t. So this is super important, okay? So what effectively we've done is we've created now, very importantly, the x and y signals. And these are going to go into the following expressions. So, so in your book, we have these super duper important expressions, right? So I'm going to put this here. So if you go to C equations 5 dash, okay, and 5 dash B, okay, and oh, no, it should be a comma. Bad, Alex. What you got is this, is the starting point. So it's not really x of t yet. So bad. So it's a kind of a predecessor. Oh, silly. So this, because there is one more step. What this is this some sort of subsampled message. Let me think. What's a way of writing this? So yeah, it's moo. So it's some sort of unit step function or a square wave that's shifted. Oh. So shucks, folks. The way I would express this, like these guys here, because I gotta do it properly. So let's say we take a pulse shape. and it's going to be equal to, yeah, so that's a unit step, so it goes up, and then we subtract off of it, yes, yeah, 2 TB. Okay, so that gives you a square pulse. Okay, cool beans. And what we got here, yeah, so this would be, the top one here would be M, so it would be sampled. So it would be sampled, so it wouldn't be T. So what this would have to be is if you sampled this thing, yeah, so here, this would have to be, so if, let's say n is equal to 0, see, this is Wyglinski thinking on the fly here. Shucks. 2n, yeah, it would be something like 2n Hmm, 2n plus 1 TB. Yeah, that's correct, right? Because so that would, no, this guy here, correct, yeah. So if n equals 0, we would already be sampling there. Okay, awesome sauce. And then what we would do is we would have this thing here, this pulse shape. And this pulse shape, now it's the argument. But it wouldn't matter because it would still have, you would start and then you would end. No, but it would matter. So it would be the value, and then would be where the pulse shape would be applied. Shucks. Yeah, so this actually would be important. So that would also be at the same point. Yep, that would be at the same point. So that would be plus 1 TB. So it would be at the sampling instant, and it would be the sampling instant, and then would be an additional 2 TB long. Okay, that's correct. So that would effectively create a rectangular pulse, and then whatever value would be at every one of the instances here at the edge of every second sample would be sampled and would be multiplied against it. Correct. And then this guy here, so that would be the expression for this waveform here. And here would be m of 2n TB, correct? And the pulse shape, correctamundo. Yeah. All right. And that would be a rectangular pulse of width 2 TB. Awesome. All right. Shucks. So it's not quite x of t yet, because that, you see, that's next. So what would happen? Okay. So that's that expression there. So I just wanted to make sure this is all golden. But what happens is in your book, okay, your book gives some expressions. It said the end result. So here's the in phase and the quadrature component of the MSK waveform. It's going to be equal to this, plus minus 1. Okay, so they do it this way. All right. Except it's not a pi. Silly Alex. So what they do here, this is sneaky too. I like this. All right. So what they do is the following. So what they do is this. And so it's a lot more elegant. So like you saw me like saying, oh my God, rectangular pulse, 2 TB wide, what you could do is also this. You might say, oh my God, how does Wyglinski do this? This is how you do it, folks. Okay, so okay, this should not be any surprises, right? Okay, so so this is standard, but these guys. So what happens is the trick they use here. Okay, very, very important trick in the book is this. That's your message signal, right? Is a +1 or is a -1 during that subsample duration. So remember, so this is that belongs to this, right? And that -1 or +1 belongs to that. So what happens is the way they do it is they take, okay, so let's say we look at T, okay? And again, very super duper important. Look at how the book does it. The period, or the frequency of this cosine and sine. These guys are not TB, they're 2 TB. So how does that look? It's going to look like this. So forget about the plus and minus 1 for now. Okay, please, please, please. Let's forget about how the plus and minus 1 looks like. So the way this works is the following. Shucks. Yeah, let's do that. So it's going to look like this. So first of all, 0, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB, 7 TB, 8 TB, 9 TB, 10 TB. Okay, and then a line here. So cosine, what is its value at 0? It is going to be equal to 1, right? So it's going to look like this. So it's like, okay, great. And it's going to go down. And it's going to do this. 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 It's going to do that. And then sine is 0. And I just want to double check because, again, I don't want to give wrong answers. It's not my thing. All right. Yeah. Here. So it's going to be boop, 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 boop. So, okay, so super cool, all right? So notice that again, cosine to sine, there's a phase offset, right? So again, here at 0 starts at 1, at 0 starts at 0. All right, now the trick, okay, the trick that that is used in that expression is this. I'm going to highlight it. So what the trick there is that the following. Like every TB, right? So again, forget about this. But every And what happens is these guys, okay, these waveforms, they either stay original or that half cycle flips during that half period, right? So remember, these are TB wide. So what ends up happening is that every 2 TB, right, 2 TB, the value of 1 or minus 1 determines whether those things flip or not. This is very, very interesting. Again, check out what the expression does. Cosine plus or minus pi t over 2 TB, okay? So that's this guy here, cosine plus or minus pi t over 2 TB. So that plus or minus 1 is that subsampled version. So what's the case here? So let's say this is my X stream, right? That's my Y stream. I want to create. So what's the first value? So that's going to be a minus 1, right? That's going to be a plus 1. Ah, shucks, no. That's going to be still a minus 1. Minus 1. That's plus 1. That's minus 1. That's minus 1. Here, that's going to be plus 1. That's going to be plus 1. That's going to be minus 1, plus 1, plus 1. Correct? Correct. Correct. So what happens? Well, this is what happens. So what ends up happening is we now apply this definition, right? So now we start applying this minus 1 plus 1 business. And so what ends up happening is when we do this process of this 1 and minus 1, right? What we end up getting is the following. So what we so if we apply this definition, like 112A, 112B, 112C, right? And we embed in it this plus 1, minus 1 stuff. So remember, that's type 2. And what I'm showing here, I just want to make sure I'm not messing folks up with between type 2 and type 1, because there's actually two different types here, folks, of MSK. Oh, really? Yeah. So just want to make sure. So okay. So let's just so what ends up happening is the following. If we do it this way, this plus 1, minus 1 stuff, right? So what ends up happening is if we have a minus 1 cosine, what are we doing, right? So what we're doing here, right, is we're effectively we're like going through this cycle, and again, the same thing is happening at the other end. So what ends up happening is the following. This is actually kind of confusing. But what is cosine plus or minus 1 2 TB equal to? Doesn't matter, right? So that's kind of a problem, right? Here, on the other hand, this is actually kind of useful. Plus or minus. So the sine term actually comes through on the sine side of things. So that's great. That's great. That's great. That's great. So this is kind of interesting. So here nothing changes. This is going to just be a cosine. Okay. Here this is sine dependent. Okay. All right. So what happens is okay, like we look at this and we say, okay, what are we looking at? Well, what happens is, like, again, we look at, like, there are two types of MSK. There's MSK type 1, and there's MSK type 2. All right. So what happens is, we have to be careful, right, between these guys, right, because they're both kind of a little bit on the different side for both, like looking at how we implement. In your book, this guy here is kind of interesting. This is figure, that is figure 5-34. So this guy is interesting because, so MSK type 1 is what I've been kind of like looking at, like with respect to this mathematical expressions. But with type 1, with type 2, this is in the like what we've been drawing here, doodling several slides ago. So here, this is going to be kind of interesting because of the fact of the when we have the plus and minus pi, right? But the other guy, okay, and then the sinusoid, that has that alternating quantity. But what we want, on the other hand, is can we come up with a way, right? And then looking at MSK type 2, okay, is can we do something where if we have a negative value, it makes it negative, and if we have a positive value, it keeps it positive. So let's go back a little bit here to this slide here, where again we have the cosine. So let's look at this a little bit. So what is it? So it starts here and okay. As you can see, this is like, okay, 0, 1, 2, 3, 4, 5, 6, 7. Ah, shucks, if I just had, let's draw this again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then cosine. So zoop, zoop. So here, the type 2 approach is this. So the type 2 approach is the following. So we could do that, or what we could do is we just take half a period, right? So that's the thing. So if we look at the equation, so this is kind of the important thing. So this waveform here, like that we saw over here, very important, because this is the kind of confusion that was like, huh, what the heck is going on? This is defined from 0 to TB, right? So we're only looking at what? We're looking on only half a period, right? Or sorry, yeah, we're only looking at half a cycle. So that's kind of the last thing. Otherwise, confusion ensues. It's like what the heck am I doing? So given that, well, where the heck am I? Oh yeah. So given that, very important, this is how it's going to look. So it's not quite this anymore, right? So now what happens is you might say, all right, so this guy, so it's not quite that, okay? It's not quite that. Remember, we are not defining that way. We're not defining the whole cosine. We are defining only half a period, okay? So this is not correct, okay? That's not correct. None of this is actually, yeah, so you're saying, why the heck is Wyglinski drawing? What we have to do is we're drawing it for just half a period. This is what we need to do. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're doing this. So again, forget about this guy. Whoop, 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 right? Again, pardon if I'm not getting to ticks. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here, the sign, boop, 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 boop. Alrighty. And then, multiply by -1, -1, +1, -1, -1. Here, +1, +1, -1, +1, +1. Correct. So what does this look like? End result. So red is x of t, and y is x of t. So very important. Can't emphasize this enough. It's not the whole cycles. It's just half a period of a cosine or a sine. So what this is going to look like, okay, so it's none of this. Z, z, okay? This is assuming we have t goes from -infinity to infinity. No, 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 no. We only look at half a period. We have this. So what is this going to look like? It's going to look like this. It's going to look like this. That's going to be like that. It's going to look like this. It's going to look like that. And here, this is going to look like that. This, 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 this. Okay. That took a while. Now, one more step. So remember, S of t is equal to this is going to be important. This is almost going to be like AM modulation. But this is going to be pretty awesome. I'm going to show why. So what this is going to look like. So now we have the envelopes. I'm going to draw them in red. And so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome. And what is the envelope again? Stop. Bad, 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 Wyglinski. Correct, correct, correct. And this is going to be, so what's going to be almost correct, except I'm out of phase by 1. So boop, and that's going to be okay. Now, very importantly, so that's 0 and that's 0, is we're going to draw, like, you know, that's the other side of the envelope. So there's going to be 180 degrees phase shift. Where? There's going to be 180 degrees phase shift here and here. So what this is going to look like at the end of the day, it's going to be pretty cool looking. It's going to look like this. So if you modulate against a cosine and you modulate against a sine at a much higher frequency, it's going to look like, it's going to squick like that, and wow, it makes another one. And notice that you have the cool transition here, right? Because it's 0. Here, we're going to get a phase change of 180 degrees. Another phase change. And what happens is we have graceful transitions between every symbol. 180 degrees phase change. So that's a beautiful way of creating graceful transitions between different bits, and they're on I and Q channels. And what happens is, this is actually pretty awesome, because what ends up happening is when you do that, you actually allow for graceful transitions. They're on I and Q channels, right? You have to be very mindful about the phase transitions. That's still going to be a bit of a pain. But what ends up at the end of the day is you get these sort of really nice waveforms that don't have any abrupt transitions between boundaries, and they combine together. Now, I just did MSK type 2 in your book. Like I pointed out, 5-112 is one cool expression there. And you saw, I was fuddling around and saying, how the heck do you deal with that? But remember again, here in that case, so the cosine, it plays a very interesting role, because in that case, what happens is, that plus minus one business it becomes a little bit of, becomes a little bit funny. But what happens is, what this MSK looks like is there's something called offset QPSK, and this is what I've been describing in the lecture notes here, right? So this is offset QPSK, right? And the same thing, if you look at the expression, this goes through the mathematics of exactly what's in the course textbook. So what you have is your passband, right? And here, again, you have your X and you have your Y. The representation is a little bit weird. This entire thing, X cosine pi over 2t, right? That should all be X, right? Just that I didn't have, remember in the doodles that I did, I had to subsample M of t. This is really what that subsample M of t is. I was just here, poor choice of nomenclature. But really, this is the in-phase sampled binary stream, right, that has been multiplied by half period of either a cosine or a sine. And this here, minus sign is missing here, is the subsampled version of M of t multiplied against half periods of sine waves, okay? And this is the representation that we have, okay? Gaussian MSK, all it is the additional filtering of a Gaussian low-pass filter. Again, the goal here with respect to the MSK, very importantly, is to minimize these weird, very abrupt transitions between every symbol. All right, so that concludes this very convoluted, sorry. No, but it is, like MSK is a little bit difficult, but check out the examples that I have posted in the Canvas website for this course. But in essence, just remember, it's like half cycles of cosines and sines. You subsample your data stream into I and Q, right? And you shift by 1 bit period. And you start multiplying every one of those half cycles by either a plus or minus 1 amplitude. And what's attractive again is, because it's half cycle, it starts at 0, ends at 0, and has a positive value. And you either get a positive half or a negative half, right, of a cycle, and then you modulate it. And what happens is that carrier frequency is always forced to 0 at multiples of 2 TB. And that, folks, is very, very amazing. All right, so that concludes lecture 23 of ECE 3311, Principles of Communication Systems.